What if you could travel so fast that time itself stretched and warped around you? Picture this racing across the cosmos at the speed of light, watching stars blur into streaks as you outpace entire galaxies. It sounds like science fiction, but the universe is already filled with objects moving at speeds so extreme they defy imagination. From neutron stars spinning hundreds of times per second to stars catapulted out of their galaxies like cosmic bullets, the universe operates on a scale of velocity that leaves our everyday experiences in the dust. Today, we're diving into the breathtaking realm of the universe's fastest objects, where the laws of physics are pushed to their limits and the ordinary rules of motion no longer apply. Think about the fastest thing you've ever seen, maybe a fighter jet breaking the sound barrier or a meteor streaking across the night sky. Now multiply that speed by millions and you're still only scratching the surface. Out there in the vastness of space, nature has crafted phenomena that move with such incredible energy they could cross the entire length of our solar system in the time it takes you to sip your coffee. Pulsars, the spinning remnants of dead stars, whip around at dizzying rates, beaming radiation like interstellar lighthouses. Hypervelocity stars, flung from their homes by the gravitational slingshot of supermassive black holes, race through the void fast enough to escape their galaxies entirely. And then there are the mysterious jets blasting from quasars, where matter is accelerated to nearly the speed of light, bending space-time itself in their wake. This isn't just about raw speed, it's about the stories these objects tell. Each one is a clue to the universe's most violent and energetic processes, from supernova explosions to collisions between black holes. By understanding how and why these objects move the way they do, we unravel the secrets of gravity, magnetism, and the very fabric of reality. So buckle up and prepare for a journey through the extremes of cosmic velocity. Over the next 30 facts, we'll explore the fastest, most mind-bending objects the universe has to offer, where the only limit is the speed of light itself. Are you ready to see just how fast things can really go? Let's begin. Neutron stars are cosmic speed demons, spinning with such ferocity that they could turn an entire revolution in less time than it takes you to blink. Born from the cataclysmic death of massive stars in supernova explosions, these collapsed cores pack more mass than our sun into a sphere no wider than a city. That extreme density means even a teaspoon of neutron star material would weigh billions of tons on Earth. But what truly defies expectations is their rotation. Some neutron stars whirl at over 700 revolutions every single second, with their surfaces hurtling through space at nearly 1/4 the speed of light. Imagine standing on the equator of one of these spinning monsters. You'd be flung into space instantly by forces far beyond anything gravity could contain. This dizzying motion doesn't just happen by chance. When a massive star collapses, its core shrinks dramatically, concentrating its original rotation into a much smaller space. It's like a figure skater pulling their arms in to spin faster, only amplified to cosmic proportions. The result is a celestial powerhouse that can generate beams of radiation so intense, we detect them as pulsars, flashing beacons across the galaxy. These pulsars serve as nature's most precise cosmic clocks, with their pulses arriving with such regularity that early astronomers initially mistook them for alien signals. The Crab pulsar, for example, spins 30 times per second, while the record-holding Pulsar Jones 748-2446 races at an astonishing 716 rotations every second. Each pulse comes from beams of light and radiation sweeping across space like a lighthouse, powered by the neutron star's unimaginable spin and crushing magnetic fields. Without this extreme velocity, these cosmic wonders wouldn't shine as brightly or reveal so much about the violent, dynamic universe we live in. Some stars don't just move fast, they move fast enough to abandon their galactic homes forever. Hypervelocity stars are cosmic outcasts flung into intergalactic space at speeds exceeding 1 million miles per hour. That's enough velocity to travel from Earth to the Moon in just under 15 minutes. The most famous of these interstellar fugitives, known as LP 4365, rockets through the void at nearly 2 million miles per hour, so fast it's leaving the Milky Way behind permanently. These stellar speedsters owe their incredible motion to the ultimate cosmic catapult, a supermassive black hole. When a binary star system wanders too close to a black hole like Sagittarius, a star at our galaxy's center, one star may get captured while the other gets violently ejected. The gravitational energy transferred during this cosmic slingshot propels the surviving star outward at velocities that defy comprehension. Picture a game of interstellar billiards where the cue ball is a black hole with 4 million times the Sun's mass, and you start to grasp the forces at play. Unlike ordinary stars that follow graceful orbits around the galactic center, hypervelocity stars trace radically different paths, straight lines cutting across the galaxy like arrows shot from a bow. Their trajectories tell the story of that violent ejection event, carrying them through interstellar gas and dust with such momentum that nothing can slow them down significantly. Within a few million years, stars like LP 4365 will cross the boundary of the Milky Way's gravitational influence, becoming true intergalactic travelers destined to wander the darkness between galaxies indefinitely. What makes these runaway stars particularly fascinating is their composition. Many, like our record-breaking LP 4365, are surviving fragments of white dwarf stars, stellar corpses that somehow endured partial destruction during their chaotic ejection. Their strange chemical signatures, rich in heavy elements but lacking hydrogen and helium, act like cosmic fingerprints revealing their explosive past. As they streak through space, these stellar refugees become natural probes of galactic structure, their light subtly altered by the gas clouds they pass through, giving astronomers an unprecedented view of our galaxy's hidden architecture. In time, all hypervelocity stars will vanish into the intergalactic void, their light fading as they drift ever further from any galaxy's embrace. But for now, they serve as breathtaking reminders that even in the seemingly orderly cosmos, nature occasionally flings its creations into the unknown with unimaginable force. Each one is a testament to the raw power lurking at the hearts of galaxies where supermassive black holes rewrite stellar destinies with a single gravitational flick. Quasars take cosmic speed to another level entirely, unleashing jets of matter that challenge the very limits of physics. These brilliant beacons, powered by supermassive black holes at their cores, blast material across space at 99.9% the speed of light, so close to light speed that time itself distorts around them. Take Quasar 3C273, one of the first ever discovered and still one of the most spectacular. Its jet stretches an astonishing 200,000 light-years through space, twice the diameter of our entire Milky Way galaxy. Yet the particles within it traverse that distance in what feels like moments from their perspective, thanks to the bizarre time-slowing effects of relativity. What fuels these extreme cosmic particle accelerators? The answer lies in the chaotic maelstrom surrounding supermassive black holes, as matter spirals inward at nearly light speed, forming a searing hot accretion disk. Intense magnetic fields channel some of that material away from the poles at unimaginable velocities. The energy released in this process defies comprehension. A single quasar can outshine 1,000 galaxies while ejecting enough material to build stars for millions of years. The particles in these jets don't just move fast, they're surfing shockwaves of pure energy, heated to billions of degrees and glowing across the entire electromagnetic spectrum. Watching these jets in action is like witnessing nature's ultimate particle collider. Electrons whipped to relativistic speeds emit brilliant synchrotron radiation as they spiral along magnetic field lines, creating the spectacular luminous structures we observe. In 3C273's case, the jet's plasma remains collimated over its entire monstrous length, barely spreading even after traveling hundreds of thousands of light years, a testament to the precision of these cosmic fire hoses. The jet's structure even reveals brighter knots where shockwaves reverberate through the outflow, marking moments when the black hole's engine surged with particular violence. What makes these jets truly mind-bending is how they warp our perception of motion. At 99.9% light speed, time dilation means that while the jet's particles experience mere minutes traversing its length, thousands of years pass in the outside universe. The particles themselves would perceive the jet as dramatically shortened due to length contraction, another consequence of Einstein's relativity. These effects aren't just theoretical quirks. They directly influence how the jets appear to us, with materials seeming to move faster than light in certain configurations due to the extreme angles and velocities involved. Quasar jets aren't merely spectacular cosmic fireworks, they are fundamental sculptors of the universe. By transporting energy and matter across intergalactic distances, they influence star formation rates in entire galaxy clusters and seed the cosmos with heavy elements. The particles they accelerate represent some of the most energetic phenomena ever detected, occasionally interacting with Earth's atmosphere as ultra-high-energy cosmic rays. 3C273's jet, like others of its kind, ultimately reminds us that even the most extreme speeds we've explored so far are just the beginning. Nature's particle accelerators operate on scales that still push the boundaries of what we thought possible. While neutron stars and quasar jets demonstrate the universe's capacity for extreme speed on massive scales, some of the fastest objects in existence are astonishingly small subatomic particles hurtling through space with enough energy to punch through planets. Cosmic rays, primarily protons and atomic nuclei, rain down on Earth continuously, some accelerated to within a hair's breadth of light speed. The most energetic among them carry as much force as a professional baseball pitch compressed into a single proton, a microscopic package of pure velocity that defies all conventional notions of motion. These particles don't just move fast, they're accelerated by some of the most violent events in the cosmos. Supernova shockwaves act as natural particle accelerators, their expanding shells of debris creating turbulent magnetic fields that can slingshot protons to 99.9% the speed of light. When a massive star explodes, the energy released doesn't just light up the galaxy, it turns the surrounding space into a chaos of electromagnetic currents capable of boosting particles to energies far beyond anything humans can replicate in particle colliders like the Large Hadron Collider. The current record holder, nicknamed the "Oh my God" particle, struck Earth's atmosphere in 1991 with an energy of 300 exa-electron volts, equivalent to a baseball traveling at 60 miles per hour, but concentrated into a single proton. To put that in perspective, the proton in question was moving so fast that from its own reference frame, the journey across our entire galaxy would take mere minutes due to relativistic time dilation. This wasn't just a fast-moving particle, it was a microscopic bullet fired from nature's own particle cannon, carrying energy millions of times greater than anything produced in our most powerful accelerators. What makes cosmic rays particularly fascinating is how they interact with our planet. When these ultra-fast particles collide with molecules in Earth's upper atmosphere, they trigger cascades of secondary particles called air showers. These sprawling particle avalanches can span kilometers by the time they reach the ground, with detectors like the Pierre Auger Observatory in Argentina capturing their faint traces. Scientists trace these showers backward like cosmic crime scene investigators, piecing together clues about the original particle's energy and direction, though pinpointing their exact origins remains one of astrophysics' greatest challenges, since magnetic fields in interstellar space twist their paths unpredictably. Some cosmic rays may have even more exotic origins than supernovas. particles at the highest energy ranges could come from active galactic nuclei, gamma-ray bursts, or as yet unknown cosmic accelerators operating at scales we've barely begun to understand. Their existence pushes the boundaries of physics, testing models of how particles interact at energies so extreme they haven't been seen since the first moments after the Big Bang. Every one that strikes Earth's atmosphere carries a message from the distant reaches of the universe written in the language of near light-speed motion. Hold onto your seat because we're about to meet the fastest spinning object ever discovered in the universe, the pulsar J1748-2446 AD. This cosmic dynamo whips around an astonishing 716 times every single second, meaning it completes more rotations in 1 minute than the hour hand on your clock does in 12 years. At its equator, material races through space at 70,000 kilometers per second, nearly 1/4 the speed of light. If you could stand on its surface, which, let's be clear, you absolutely couldn't, you'd experience forces so intense they'd flatten you into subatomic particles before you even realized what was happening. What keeps this stellar speedster from tearing itself apart? The answer lies in the pulsar's mind-bending density. Packing more mass than our Sun into a sphere just 20 kilometers across, its gravity is so strong that the surface escape velocity reaches roughly 1/3 the speed of light. That means even at 70,000 kilometers per second, the material at its equator still can't overcome the pulsar's gravitational grip. It's like trying to throw a ball off a planet where the atmosphere itself would weigh billions of tons per square inch. The forces involved are simply beyond human scales of reference. This pulsar's incredible spin didn't happen by accident. Astronomers believe it gained its record-breaking rotation through a cosmic partnership gone wrong. Originally part of a binary system, PSR J1748-2446 AD likely siphoned material from its companion star, transferring angular momentum in the process. Imagine a figure skater pulling in their arms to spin faster, only instead of arms, it's stealing entire suns worth of plasma to rev itself up. The influx of matter acted like a natural particle accelerator, spinning the pulsar up to velocities that push the limits of what astrophysics says should be possible. What's truly remarkable is how this pulsar challenges our understanding of neutron star structure. At its equator, the rotational velocity approaches the point where relativistic effects should start tearing spacetime itself apart, yet the pulsar remains intact. Its stability suggests neutron star crusts might be far stronger than previously thought, possibly with a crystalline structure reinforced by nuclear forces we've yet to fully comprehend. Some theories even propose exotic states of matter in its core, where neutrons dissolve into a soup of quarks generating pressures 100 trillion times greater than Earth's atmosphere. PSR J1748-2446 AD isn't just breaking records, it's serving as a natural laboratory for extreme physics. The lighthouse-like beams of radiation it emits, which we detect as radio pulses, allow scientists to test Einstein's theory of general relativity with unprecedented precision. Every rotation creates subtle vibrations in spacetime called gravitational waves, ripples that new observatories are just beginning to detect. This pulsar's spin is so stable that its pulses arrive with atomic clock-like regularity, yet when it occasionally glitches, suddenly spinning even faster for fractions of a second, it gives astronomers rare glimpses into the turbulent dynamics beneath its surface. In the grand cosmic scheme, this hyper-spinning pulsar represents nature pushed to its absolute limits. It's a reminder that even in a universe governed by physical laws, there exist corners where matter behaves in ways we're only beginning to understand. Every pulse from PSR J1748-2446 AD carries information about the most extreme states of matter, the strongest gravitational fields, and the very fabric of spacetime warped by rotation. For now, it holds the title as the fastest spinning object we know, But somewhere out there, the universe may have already forged something even more extreme. Even black holes, those cosmic vacuum cleaners we imagine as stationary traps, can become the universe's ultimate speed demons when conditions turn violent. Meet 3C186, a supermassive black hole racing through intergalactic space at 4.7 million miles per hour, fast enough to travel from Earth to the Moon in under 3 minutes. This cosmic bullet, weighing 1 billion times more than our Sun, isn't just moving, it's being violently ejected from its home galaxy by the recoil of gravitational waves generated during one of the most catastrophic events imaginable, the collision of 2 supermassive black holes. Picture the aftermath of this cosmic car crash. When 2 gargantuan black holes spiral inward and merge, their collision doesn't just create ripples in space-time, it can kick the newborn black hole clear out of the galactic neighborhood. The physics behind this is staggering. As the black holes finalize their merger, gravitational waves carry away momentum asymmetrically, launching the remaining black hole in the opposite direction like a rocket firing its engines. For 3C186, this recoil was so powerful it overcame the gravitational pull of an entire galaxy cluster, sending it careening through intergalactic space with enough speed to escape permanently. What makes these runaway black holes truly spectacular are the cosmic breadcrumbs they leave behind. As 3C186 plows through intergalactic gas, it drags along a streamer of stars and glowing plasma stretching over 35,000 light-years, like a cosmic jet ski trailing luminous spray. Telescopes capture this phenomenon as a quasar that's conspicuously offset from its host galaxy's center, with the black hole's path illuminated by shocked gas heating up to millions of degrees. Simulations show these trajectories aren't straight lines but complex curves, as the black hole interacts with dark matter halos and other large-scale structures during its escape. The speed record for these intergalactic fugitives keeps climbing as astronomers discover more candidates. Another contender, CID-42, shows evidence of a black hole moving at nearly 5 million miles per hour, its departure so violent it left a visible cavity in the host galaxy's star distribution. The energy required for such motion is incomprehensible, equivalent to 100 million supernovas exploding simultaneously in the same direction. Yet this isn't science fiction. It's the universe demonstrating how even the most massive objects can become projectiles when Einstein's physics takes the wheel. Unlike hypervelocity stars that eventually fade into darkness, runaway black holes remain visible for billions of years as they continue feeding on intergalactic gas. 3C186's quasar glow ensures we can track its progress long after it's left its home galaxy far behind. Its very existence challenges assumptions about galaxy evolution, proving that the engines powering these brilliant beacons aren't always anchored to galactic centers. Some may wander the cosmic voids indefinitely, becoming rogue quasars lighting up the emptiness between galaxies. This phenomenon also gives astronomers a unique opportunity to study gravitational wave physics on cosmological scales. The kick velocity reveals details about the original black hole merger, their mass ratios, spin orientations, and the exact moment of collision. Future gravitational wave observatories might even detect these extreme recoil events directly, matching them to runaway black holes spotted by telescopes. For now, each new discovery like 3C186 expands our understanding of how the universe redistributes its most extreme objects, flinging them across space with forces that make even supernovas look gentle by comparison. Gamma-ray bursts unleash energy so extreme they make supernovas look like firecrackers. Take GRB 080916C, one of the most powerful ever recorded. When it erupted from a distant galaxy, it unleashed a jet of material screaming through space at 99.9999% the speed of light. That's so close to light speed, if you could ride one of those particles, your watch would tick just once while centuries passed back on Earth. The sheer scale of energy here is incomprehensible. In just 23 seconds, this single burst emitted more gamma rays than our Sun will produce across its entire 10 billion-year lifetime, equivalent to converting the Sun's entire mass directly into pure energy. What propels material to such ludicrous velocities? The answer lies in the death throes of a very particular kind of star. When a massive, rapidly rotating star collapses, it doesn't just form a neutron star, it creates a newborn black hole surrounded by a swirling maelstrom of superheated gas. Magnetic fields twist this accretion disk into twin jets that punch through the collapsing star like cosmic blowtorches, funneling material outward with pressures a quadrillion times greater than Earth's core. The jets aren't just fast, they're narrow, focused to within a few degrees, which concentrates their energy like water through a fire hose. This collimation is key. Without it, the material would disperse too quickly to reach such extreme velocities. GRB 080916C's afterglow revealed another bizarre relativistic quirk. As the jet plowed through interstellar gas, it created shockwaves that emitted light at different energies depending on the observer's angle. Higher energy gamma rays arrived at Earth before lower energy ones, a phenomenon called spectral lag that only makes sense if the jet's material is moving with bulk Lorentz factors in the thousands. To put that in perspective, at these speeds, time dilation means the particles experience just minutes while traversing distances that light itself would take years to cross. The burst's energy profile reads like something from mythology. Its prompt emission phase, the initial gamma ray flash, peaked at energies around 13 billion electron volts, while later observations detected photons with energies up to 94 billion electron volts. That's particle physics territory, comparable to what our largest human-made accelerators produce, except here nature generated it naturally across interstellar space. If such a burst occurred within our galaxy, even tens of thousands of light-years away, the radiation could strip Earth's ozone layer and trigger mass extinctions. Thankfully, GRBs this powerful are rare, occurring perhaps once per million years in any given galaxy. What makes these events particularly fascinating is how they serve as cosmic particle accelerators on scales we could never replicate. The same processes that create gamma-ray bursts also generate ultra-high-energy cosmic rays, some of which eventually reach Earth. Their afterglows act as backlit screens, revealing the composition of distant galaxies through absorption lines. Each burst is effectively a space-time beacon, its light stretched and distorted by the expanding universe, giving us snapshots of cosmic history. GRB 080916C's light traveled for 12.2 billion years before reaching us, meaning we witnessed a cataclysm that occurred when the universe was just 1/7 its current age. Among the countless stars streaking through our galaxy, one stands out as the undisputed speed champion S5HV-S1. This stellar bullet rockets through space at 1,700 kilometers per second, or roughly 3.8 million miles per hour. At that velocity, it could travel from Earth to the Moon in just 6 minutes, a trip that typically takes spacecraft 3 days. What's even more astonishing is that this star isn't just passing through. It's on a one-way journey out of the Milky Way entirely, flung into intergalactic space with enough speed to escape our galaxy's gravitational pull forever. The story behind this cosmic fugitive begins 5 million years ago near Sagittarius, a star, the supermassive black hole at our galaxy's core. Astronomers reconstruct its trajectory like detectives piecing together a celestial crime scene. All paths lead back to an extraordinarily close encounter with the black hole's unimaginable gravity. Here's how the escape unfolded. S5HV-S1 likely originated as part of a binary star system that wandered too close to Sagittarius, a star's event horizon. The black hole's tidal forces captured one star while violently ejecting the other, transferring enormous kinetic energy in what astrophysicists call the Hill's mechanism. Picture a cosmic slingshot where the rubber band is spacetime itself. and the payload is an entire star accelerated to 1% the speed of light. What makes S5HVS1 particularly remarkable is its pristine condition. Unlike other hypervelocity stars that show signs of distortion from their traumatic ejection, this one appears almost untouched, a testament to the precision of gravitational physics at work. Its spectral signature reveals a hydrogen-richer type star about 2.5 times more massive than our Sun, shining with a steady blue-white light as it cuts through the galaxy's halo. The lack of atmospheric disturbance suggests its acceleration happened almost instantaneously, like a stone skipping across a pond rather than being dragged through water. Tracking this star's movement offers scientists unprecedented insights into Sagittarius, a star's environment. The ejection energy required to propel S5HVS1 to its current velocity implies the black hole must have been particularly active 5 million years ago, a period coinciding with evidence of a massive flare that left scars on the surrounding gas clouds. This correlation turns a single runaway star into a cosmic timestamp, helping astronomers reconstruct the black hole's historical activity cycles. The star's trajectory also serves as a measuring stick for the Milky Way's dark matter distribution, as subtle deviations in its path could reveal unseen mass concentrations. As S5HVS1 continues its lonely journey, it carries with it secrets about the extreme physics occurring just outside a black hole's event horizon. Within another 10 million years, it will cross the boundary where the Milky Way's gravity can no longer pull it back, becoming a permanent exile in the darkness between galaxies. For now, it streaks through our night sky like a cosmic arrow, silent, unstoppable, and bearing witness to the most powerful gravitational kick ever measured in our celestial neighborhood. The Sun's corona isn't just a shimmering halo of light. It's a seething ocean of plasma where waves crash at speeds that would cross the continental United States in under 5 seconds. During violent solar eruptions called coronal mass ejections, these plasma waves rocket outward at over 1,000 kilometers per second, carrying enough energy to power global civilization for 20,000 years. The footage is mesmerizing, vast ribbons of superheated gas arcing millions of kilometers into space, accelerated by magnetic forces so intense they warp the very fabric of the solar atmosphere. What makes these plasma waves particularly remarkable is how they form. When the Sun's tangled magnetic field lines suddenly snap and realign, a process called magnetic reconnection, they release energy equivalent to billions of hydrogen bombs in seconds. This explosion launches a shock wave through the corona, heating plasma to tens of millions of degrees and propelling it outward in a self-sustaining avalanche. The fastest waves create visible ripples across the Sun's surface, like tsunamis of fire stretching 3 times Earth's diameter, their motion captured in stunning detail by NASA's Solar Dynamics Observatory. These aren't just beautiful cosmic phenomena, they're direct drivers of space weather that can wreak havoc on Earth. When particularly intense waves reach our planet, they compress Earth's magnetic field, triggering geomagnetic storms capable of frying satellites, disrupting power grids, and creating auroras visible as far south as the tropics. The infamous Carrington event of 1859, sparked by an extreme coronal mass ejection, produced plasma waves so powerful they electrified telegraph lines and set papers ablaze in telegraph offices. A similar event today could cause trillions in damage to our technology-dependent civilization. The physics behind these waves reveals why they're so destructive. Unlike sound waves or water waves, coronal plasma waves are magneto-hydrodynamic, meaning they're governed by the interplay between electrically conducting plasma and magnetic fields. This allows them to transport energy far more efficiently than ordinary matter, with particles surfing the wavefronts at relativistic speeds. Recent observations show these waves can even reshape the Sun's global magnetic field, sometimes triggering chains of eruptions across different regions like falling dominoes. Understanding these plasma tsunamis isn't just about disaster preparedness, it's a window into fundamental cosmic processes. The same wave mechanics operate in distant quasars, supernova remnants, and even Earth's experimental fusion reactors. By studying how energy propagates through the corona, solar physicists are decoding universal principles of magnetized plasmas that govern everything from auroras to the growth of galactic jets. Each eruption is a natural laboratory demonstrating how magnetic forces can transform gentle stellar breezes into the universe's most formidable particle accelerators. Cancri isn't just a binary star system, it's a cosmic ballet performed at speeds that would make a fighter jet look stationary. These two white dwarfs, the dense leftover cores of dead stars, whip around each other at 500 kilometers per second, completing a full orbit in just 5.4 minutes. That's faster than the International Space Station circles Earth, and so rapid that if you stood on one of these stars, which, given their crushing gravity and scorching temperatures, would be impossible, the other would streak across your sky like a hyperactive firefly, appearing and disappearing every few moments. What makes this system truly extraordinary is how it pushes Einstein's theory of general relativity to its limits. The star's breakneck motion generates ripples in space-time itself, gravitational waves that drain energy from their orbit. Every second, Cancri loses enough orbital energy to power human civilization for an entire year, purely through these invisible space-time distortions. Within the next 300,000 years, a blink in cosmic terms, this energy loss will bring the stars spiraling together in a spectacular collision, likely creating a massive supernova or forming a neutron star. The discovery of Cancri's ultra-fast orbit solved a 15-year astronomical mystery. Initially detected in 2001 as an X-ray source pulsing every 5.4 minutes, astronomers debated whether the signal came from a single spinning star or something more complex. Only in 2009 did careful analysis of its light variations confirm the truth. We were seeing two separate stars orbiting so close together that their surfaces would nearly touch if placed in our solar system. Their mutual gravitational pull distorts each white dwarf into egg-like shapes, creating dramatic brightness changes with each rotation that serve as a precise cosmic clock. This system isn't just a curiosity, it's a goldmine for testing fundamental physics. The star's decaying orbit matches Einstein's predictions for gravitational wave energy loss with unprecedented precision, providing indirect confirmation of phenomena now directly detected by observatories like LIGO. Cancri's gravitational waves, though too faint for current detectors to observe directly, will become a prime target for future space-based observatories like LISA. When launched, this trio of spacecraft will use laser beams spanning millions of kilometers to hunt for the subtle spacetime ripples from extreme systems like Cancri, effectively turning them into cosmic laboratories for probing gravity's nature. The white dwarfs themselves hold equally fascinating secrets. Each packs roughly half the Sun's mass into a sphere the size of Earth, meaning a teaspoon of their material would weigh as much as an elephant. Their incredibly tight orbit suggests they've already transferred substantial mass between them, likely during a previous red giant phase when one star swelled and spilled material onto its companion. Now locked in this frantic dance, they showcase how binary stars can evolve into bizarre configurations unlike anything single stars could produce. As Cancri continues its rapid decay, it offers astronomers a rare opportunity to study the final stages before a stellar merger. Most cosmic events of this magnitude happen too quickly to observe in detail. Supernovas, for example, give little warning before exploding. But here, we can watch the entire process unfold over human timescales, like having front row seats to a slow-motion collision of stellar titans. Each orbit brings them 40 centimeters closer, a measurable change that lets us track their inevitable fate with growing precision. For astrophysicists, it's like watching the universe's stopwatch count down to one of its most violent and luminous events. Humanity's most powerful particle accelerators can hurl electrons at 99.999999% the speed of light, so close to light speed that from the particle's perspective, a cross-country trip would take less time than a heartbeat. At CERN Large Hadron Collider, protons complete 11,000 laps around its 27-kilometer ring every second, achieving energies that would make them glow brighter than the sun if they were visible. Yet even this staggering achievement pales beside nature's own particle accelerators, where cosmic forces routinely propel particles to velocities that make our best technology seem like child's play. Take the Crab Nebula, the remnants of a supernova recorded by Chinese astronomers in 1054. Its swirling filaments act as a natural particle collider spanning 10 light-years, where electrons spiral around magnetic fields at 99.9999% light speed, just one decimal place shy of CERN record, but operating continuously for nearly a millennium without human intervention. These cosmic electrons generate eerie blue synchrotron radiation as they race through the nebula's tangled magnetic fields, their paths curving so tightly that they emit X-rays visible across the galaxy. Unlike controlled accelerator experiments, the Crab's particles face no vacuum chambers or precisely tuned magnets, just the chaotic aftermath of a star's violent death, where turbulence and shockwaves replace engineering with raw astrophysical power. The energy scales involved reveal why nature still holds the upper hand. While CERN protons reach 7 tera-electron-volts, electrons in supernova remnants like G106.3-136 have been clocked at 1 peta-electron-volt, 1,000 times more energetic. Some cosmic rays, likely accelerated by similar processes, carry energies exceeding 100 exa-electron-volts, millions of times beyond anything producible on Earth. These particles owe their extreme speeds to diffusive shock acceleration, a process where they bounce like pinballs between converging shock waves in the turbulent debris of exploded stars. Each crossing of the shock front boosts their energy fractionally, but over centuries, this natural Fermi acceleration can propel particles to velocities approaching physics' absolute limit. What makes cosmic accelerators truly humbling is their scale and endurance. While human colliders operate for decades at most, supernova remnants like Cassiopeia have been refining their particle beams for 350 years, their shock waves expanding through interstellar space at 15,000 kilometers per second. The radio emissions from these accelerating electrons form intricate lace-like patterns across the sky, visible proof that nature's version of the Large Hadron Collider requires no steel or superconductors, just the explosive energy of a dying star and the patience of deep time. Yet there's a crucial difference between man-made and natural accelerators that reveals why both remain essential. Laboratory experiments offer pristine control, allowing scientists to isolate specific particle interactions with precision impossible in the messy astrophysical realm. Cosmic accelerators, by contrast, demonstrate how particles behave in real-world conditions, where magnetic turbulence, dust clouds, and overlapping shock fronts create environments far more complex than any vacuum chamber. Together, they form complementary frontiers in humanity's quest to understand matter's ultimate speed limits, proving that even our most advanced technology still takes cues from the universe's original particle physicist, pure, unbridled cosmic chaos. TOI 2109b isn't just a fast exoplanet, it's a world living on the edge of disintegration, racing around its star so quickly that a full year there lasts less than an Earth day. This hot Jupiter completes each orbit in just 16 hours, screaming through space at 800,000 kilometers per hour. To put that speed into perspective, if Earth moved this fast, we'd circle the Sun every 21 days instead of 365. But velocity isn't the only extreme here. Surface temperatures on this bloated gas giant soar to 3,500 degrees Celsius, hot enough to vaporize iron and turn rock into molten rivers of lava. What keeps this planet tethered to its star despite such blistering speeds? The answer lies in an intimate cosmic dance gone wrong. TOI-2109b orbits so close to its host star that the two are nearly touching, separated by just 2.4 million kilometers, barely 6 times the distance between Earth and the Moon. At this proximity, tidal forces have stretched the planet into an elongated football shape, with its atmosphere boiling away into a comet-like tail of superheated gas. The star's gravity pulls so strongly on the planet's near side that it creates permanent seismic upheavals, churning the interior like a pot of molten metal on a furnace. The heat generated by this tidal stretching defies earthly comparisons. While friction from ocean tides on Earth produces barely noticeable warmth, TOI-2109b's entire bulk gets kneaded like dough, converting orbital energy into thermal radiation visible across interstellar space. This process, called tidal heating, operates on a scale that liquefies the planet's upper layers, creating supersonic winds that carry this scorching heat from the permanent day side to the cooler night side, except there is no true night side. The planet is likely tidally locked, with one hemisphere perpetually facing the star while the other glows dull red from internal heat redistribution. Astronomers discovered this extreme world through minute dips in its star's brightness, the telltale signature of a planet transiting across the stellar disk. But TOI-2109b stood out immediately because these dips occurred every 16 hours like clockwork, revealing an orbit tighter than any previously known for a gas giant. Follow-up observations showed the planet's atmosphere puffing outward from the intense heating, creating an extended envelope of ionized gas that makes it appear nearly 25% larger than Jupiter despite having comparable mass. Spectral analysis revealed sodium and potassium vapor in its atmosphere, elements that would normally condense into clouds on cooler worlds but here remain perpetually dissolved in a superheated soup. This exoplanet's existence challenges our understanding of planetary formation and survival. Conventional models suggest gas giants form farther out in their solar systems before migrating inward, but none predicted they could stabilize so close to their stars without being torn apart. TOI-2109b may represent the final fiery chapter in a gas giant's life, doomed to spiral ever closer until the star's gravity rips it apart, creating a temporary debris disk before vanishing entirely. Right now, it's losing about 10 Earth masses worth of atmosphere every billion years, its outer layers evaporating into space like steam from a boiling kettle. What makes this discovery particularly valuable is how it serves as a natural laboratory for studying atmospheric escape. The Hubble Space Telescope has detected helium gas streaming from the planet at speeds exceeding 35,000 kilometers per hour, offering real-time observations of how planets die under extreme stellar bombardment. Similar processes likely shaped the evolution of early solar systems, where countless worlds may have been reduced to cinders before life could emerge. TOI-2109b gives us a front-row seat to this cosmic demolition derby, showcasing the violent forces that sculpt planetary systems across the galaxy. While this scorched world might seem inhospitable beyond imagination, its very extremes make it a Rosetta Stone for understanding planetary limits. Future telescopes like the James Webb Space Telescope could analyze its atmosphere for metals vaporized from what might once have been a solid core, a ghostly remnant of the planet's cooler past. Every orbit brings it incrementally closer to its star, each pass stripping away more of its identity until one day, perhaps millions of years from now, it will cross the point of no return and become just another meal for its voracious stellar companion. Until then, TOI-2109b races against time itself, an astronomical speedster burning bright in its final cosmic lapse. Messier 82 isn't just a galaxy, it's a cosmic hurricane blasting superheated gas into intergalactic space at 2,000 kilometers per second. These aren't ordinary stellar winds, but titanic outflows powerful enough to reshape entire galaxies, driven by the collective fury of hundreds of exploding stars. Known as starburst galaxies, these celestial powerhouses like Messier 82 form stars at rates hundreds of times faster than our Milky Way, creating environments so volatile they essentially cook themselves from the inside out. Every massive star born in these frenzied nurseries lives fast and dies young, culminating in supernova whose shockwaves combine like synchronized detonations to propel gas outward at speeds approaching 1% of light speed. The mechanics behind these galactic winds operate on scales that dwarf anything in our solar system. When clusters of supernova erupt in quick succession, as often happens in starburst regions, their expanding shells merge into a single colossal bubble of million-degree plasma. This superheated gas punches through cooler surrounding material, accelerating further as it escapes the galaxy's gravitational grip. The result is a bipolar outflow stretching tens of thousands of light-years, visible in X-rays and radio emissions as a pair of colossal chimneys venting star-forming material into the cosmos. In Messier 82's case, these fountains carry enough mass each year to build 10,000 suns, yet they're moving so fast that most of this material will never fall back into the galaxy. What makes these winds truly transformative is how they redistribute the building blocks of future stars across cosmic distances. Heavy elements forged in stellar cores, carbon, oxygen, iron, get swept up in the outflow and deposited into intergalactic space like seeds scattered by a celestial storm. Telescopes have detected these metallic fingerprints in the otherwise pristine gas between galaxies, proving starburst winds serve as nature's primary transporters of enriched material. Some models suggest our own Milky Way may have experienced periods of starburst activity early in its history, with similar winds potentially explaining certain chemical abundances we observe today. The sheer energy involved defies terrestrial comparison. A single starburst galaxy's wind can carry the kinetic equivalent of several supernova exploding every year for millions of years, enough energy to reionize vast swaths of the early universe. These outflows don't just move gas, they sculpt their host galaxies by halting star formation through brute force. As the wind evacuates molecular clouds from the galactic disk, it starves future stellar nurseries of their raw material, effectively capping how large the galaxy can grow. This self-regulating mechanism may explain why we don't see many extremely massive galaxies, despite the universe having billions of years to build them. Astronomers study these phenomena using an array of techniques that reveal different layers of the chaotic outflow. X-ray telescopes capture the hottest plasma at tens of millions of degrees, while infrared instruments trace cooler dust entrained in the wind. The Hubble Space Telescope has even caught glimpses of massive gas clouds being shredded by the outflow's sheer velocity, their fragments stretched into glowing streamers like cosmic banners flapping in a hypervelocity breeze. Each observation adds pieces to the puzzle of how galaxies evolve through these violent phases, cycling matter between stars, interstellar space, and the cosmic voids beyond. Perhaps most remarkably, these winds may hold clues to one of cosmology's biggest mysteries: how galaxies communicate across vast distances. Some theories suggest starburst outflows from early galaxies helped trigger star formation in neighboring systems by compressing gas as they plowed through intergalactic space. Others posit that the metals dispersed by these winds made it possible for later generations of stars, and potentially life-bearing planets, to form with the necessary heavy elements. Messier 82's furious winds, visible even in amateur telescopes as a streak of smoky light, remind us that the universe's fastest phenomena aren't just spectacular, they're essential architects of the cosmic landscape we inhabit today. At the heart of an unassuming binary system 28,000 light-years away, a monstrous black hole spins so fast it warps spacetime into knots. GRS 1915+105 isn't your average collapsed star. This microquasar's event horizon whirls at 1,150 rotations every second, dragging the very fabric of reality around it at 92% the speed of light. Picture a cosmic blender with enough gravitational might to twist the paths of photons into spirals where the normal rules of geometry no longer apply. This extreme rotation creates one of relativity's most dramatic phenomena, frame dragging. As the black hole spins, it pulls surrounding spacetime along like thick syrup clinging to a spinning spoon. Any spacecraft venturing near would find itself whipped around uncontrollably, its trajectory altered not by any physical force but by the distortion of space and time itself. The effect is so pronounced that particles orbiting close enough experience something extraordinary. They get swept into co-rotation, forced to move with the black hole's spin regardless of their original velocity. It's as if the universe itself becomes a vortex with this gravitational monster at its center. What makes GRS 1915+105 particularly fascinating is how we measure its spin. Scientists track X-ray flickers from its accretion disk, the superheated matter spiraling toward oblivion, to detect subtle distortions caused by frame dragging. The innermost stable circular orbit, the last possible path where matter can circle before plunging in, lies incredibly close to the event horizon due to the extreme spacetime warping. This proximity reveals the black hole's rotation through telltale distortions in the X-ray spectrum, like cosmic fingerprints left by relativistic effects. The energy unleashed by this rotation could power civilizations. Magnetic fields twisted by the black holes spin launched jets of plasma at near light speed, stretching over light years and glowing across the electromagnetic spectrum. These jets aren't just spectacular cosmic fireworks, they're proof that rotational energy can be extracted from black holes themselves, a process first theorized by Roger Penrose and now observed in action. If we could harness just a fraction of this energy, it would dwarf all power sources humanity has ever created combined. Yet this dizzying spin also marks a cosmic countdown. As GRS 1915+105 continues feeding on its companion star, its rotation inches closer to the theoretical maximum, a limit where spacetime around it becomes so distorted that the concept of rotation loses meaning. Some theories suggest such extreme black holes may develop ergorgons where nothing can remain stationary, not even light, forcing everything to move with the black hole's rotation in a perpetual cosmic waltz. What we're witnessing here is essentially gravity's ultimate victory dance, a collapsed star so dense and so fast that it twists the universe's rules into pretzels. Every new observation of this microquasar pushes our understanding of physics to the brink, revealing just how strange reality becomes when rotation and gravity team up at cosmic scales. Deep in the direction of the constellations Centaurus and Hydra, something massive is pulling at our galaxy with irresistible force, a gravitational enigma astronomers call the Great Attractor. Picture this: our entire Milky Way, along with countless other galaxies, is racing toward this invisible cosmic focal point at 600 kilometers per second, fast enough to cross the United States in just 7 seconds. That's nearly 2 million miles per hour, yet we can't see what's dragging us forward through the universe. This mysterious region holds the mass of tens of thousands of Milky Ways, bending spacetime so profoundly that it redirects the motion of our entire galactic neighborhood. The Great Attractor's pull reveals itself through subtle distortions in cosmic expansion. Normally, galaxies move apart as the universe expands, but in this region, hundreds of galaxies stream against the cosmic tide, their paths converging like leaves caught in a whirlpool. Infrared telescopes piercing through the Milky Way's dusty plain have revealed part of this hidden structure, a supercluster of galaxies called the Norma Cluster, sitting near the Great Attractor's core. But even this concentrated mass can't fully explain the staggering gravitational pull we observe, leading scientists to suspect an even larger structure lies beyond, obscured by our own galaxy's interstellar dust. This cosmic current carries dire implications for our galactic future. The Milky Way isn't just moving toward the Great Attractor, it's on an unavoidable collision course with our neighboring Andromeda galaxy first, an event set to unfold in about 4 billion years. But the Great Attractor ensures this won't be the end of our journey. Both galaxies, now merged into one, will continue plunging deeper into this gravitational well, eventually joining the hundreds of other galaxies piling up in what astronomers call the Laniakea supercluster, a vast filament of galaxies spanning 500 million light-years, all flowing toward the same unseen destination. What makes this phenomenon particularly unsettling is how little we truly understand about our place in the cosmic flow. The Great Attractor might not even be the ultimate destination. Recent studies suggest an even more massive structure called the Shapley supercluster, lying 800 million light-years beyond it, could be the true gravitational anchor reshaping our corner of the universe. Each new observation peels back another layer of this mystery, revealing a universe far more interconnected and dynamic than we ever imagined, where entire galaxies become mere specks caught in currents of dark matter and gravity we're only beginning to map. As we hurtle toward this unknown future, the Great Attractor serves as a humbling reminder that even our majestic galaxy is no more than a raft adrift on cosmic tides, subject to forces that dwarf human scales of time and space. Its relentless pull challenges our understanding of the universe's large-scale structure, proving that the emptiest-looking voids might hide the most significant drivers of our motion through the cosmos. One thing is certain: wherever this invisible hand is guiding us, the journey will reshape our galactic home in ways we can scarcely predict. Amid the countless asteroids drifting through our solar system, one stands out as the undisputed speed champion, 2021 PH27. This city-sized rock doesn't just orbit the Sun, it races around it in a blistering 88-day sprint, reaching velocities of 106 kilometers per second at its closest approach. That's fast enough to cross the Atlantic Ocean in under a minute, or travel from Earth to the Moon in just over an hour. But what makes this asteroid's motion truly extraordinary isn't just its raw speed, it's the extreme conditions that velocity creates, turning this rocky body into a cosmic pressure cooker on the brink of self-destruction. The secret behind 2021 PH27's record-breaking orbit lies in its elongated path, which brings it closer to the Sun than any known asteroid except Mercury. At perihelion, it swoops within 20 million kilometers of our star, so close that solar radiation heats its surface to nearly 500 degrees Celsius, hot enough to melt lead. Yet just weeks later, at its farthest point, temperatures plummet to -200 degrees, creating thermal shocks that fracture the rock like glass dipped in liquid nitrogen. These extreme swings aren't just surface-level phenomena. They penetrate deep into the asteroid's structure, causing expansion and contraction that could eventually tear it apart. Astronomers discovered this solar daredevil in 2021, spotting its faint reflection against twilight skies using the powerful dark energy camera in Chile. Tracking its path revealed an orbit tilted 32 degrees relative to the solar system's plane, a trajectory suggesting it might be the remnant of a comet that lost its volatile ices after countless close solar passes. Now reduced to a rocky skeleton, 2021 PH27 experiences gravitational forces so intense during perihelion that Einstein's theory of general relativity subtly alters its orbit, causing its closest approach to shift by about 1 arcminute per century, a small but measurable effect that wouldn't exist for slower-moving bodies. The asteroid's breakneck velocity also creates unique observational challenges. Moving 3 times faster than typical near-Earth asteroids, it blurs in telescopic images like a race car caught in a long-exposure photograph. This speed, combined with its proximity to the sun's glare, means we only get brief windows to study it during dawn and dusk. Yet these fleeting glimpses have revealed tantalizing clues, spectral data, suggesting a surface rich in silicate minerals, baked to a crisp by relentless solar bombardment, with possible metal veins that might explain how it's held together despite the punishing environment. What makes 2021 PH27 particularly intriguing is its cosmic expiration date. Current models suggest it has perhaps a few million years left before gravitational perturbations from Mercury or Venus send it careening into the Sun, or worse, fling it outward into the icy depths of the solar system. Every close pass strips away more material, with thermal imaging showing a faint dust trail that could be the early stages of disintegration. This gradual self-destruction offers a preview of what awaits most asteroids that venture too close to stellar furnaces, their rocky bodies unable to withstand the combined assault of heat, gravity, and velocity. For planetary scientists, this speedy asteroid serves as a natural laboratory for studying material resilience under extreme conditions. Its behavior hints at how planetary building blocks behave when pushed to their thermal and gravitational limits, knowledge crucial for understanding not just our solar system's evolution, but also the fate of exoplanets orbiting dangerously close to their host stars. As 2021 PH27 continues its blistering dance with the Sun, each orbit brings it closer to oblivion, reminding us that even in the seemingly stable cosmos, velocity can be both a spectacle and a death sentence. Velocity isn't just another flickering point of light, it's a cosmic particle cannon aimed directly at Earth, shooting a jet of plasma so fast that it appears to break the universe's speed limit. This Quasar, a supermassive black hole roughly 900 million times more massive than our Sun, demonstrates one of relativity's most mind-bending tricks, particles moving at 99.9% light speed that seem to travel faster than light from our perspective. The illusion occurs because the jet's material races toward us almost as fast as the light it emits, compressing the arrival time of photons in a relativistic sleight of hand that turns physics inside out. What makes Velocity's jet particularly mesmerizing is how we're viewing it head-on. Unlike quasars with tilted jets that show their structure from the side, this Quasar's beam points straight at Earth like a lighthouse with its spotlight trained directly on us. As plasma blobs accelerate down the jet's magnetic funnel, their apparent motion across the sky far exceeds light speed, not because they're actually breaking cosmic rules, but because each successive blob is emitted slightly closer to us than the last. Imagine a sprinter dashing toward you while flipping on a flashlight every few steps. The light from later flashes has less distance to travel, making the beam's movement appear faster than any individual photon. The numbers involved stretch credulity. Time-lapse observations revealed jet components seemingly separating at 15 times light speed, streaks of energy hurtling across 30,000 light-years of space in mere months. This superluminal illusion is no graphical glitch, it's the direct consequence of material moving at 0.9999 times light speed combined with our nearly face-on viewing angle. Relativity's time delay effects stack up dramatically at these velocities. While the plasma takes years to traverse the jet's length from its own perspective, we see the journey compressed into weeks due to the extreme Doppler boosting of its light. Visualizing this requires peeling back layers of relativistic weirdness. As particles in the jet accelerate, their light gets concentrated into a narrow cone pointed forward, like headlights brightening as a car speeds toward you. This Doppler boosting makes Velocity's jet appear hundreds of times brighter than it would from the side, while simultaneously redshifting the light from any receding material to near invisibility. The effect is so potent that the jet's gamma-ray emission can briefly outshine every other object in its host galaxy combined, flickering unpredictably as new shockwaves ripple through the outflow. What truly sets Velocity apart is how cleanly it demonstrates these phenomena. Unlike messier active galaxies where multiple jets crisscross or interact with gas clouds, this blazar offers a relatively unobstructed view straight down the particle accelerator's barrel. Radio telescopes have tracked individual plasma knots spiraling along magnetic field lines at 99.99% light speed, their paths twisted by the black hole's immense rotation into corkscrew patterns visible across light years. These observations provide real-time confirmation of Einstein's century-old predictions, showing how magnetic fields can channel and focus relativistic particles with laser-like precision. The practical implications extend far beyond one exotic object. Blazars like velocities serve as natural laboratories for studying how matter behaves under the most extreme accelerations the universe can produce. Their jets likely generate ultra-high-energy cosmic rays that occasionally strike Earth's atmosphere, and understanding their mechanics could reveal how particles reach energies 1,000,000 times beyond anything human colliders achieve. Every flicker from this distant black hole's jet carries information about the fundamental forces shaping our universe, distorted by relativistic effects, amplified by our privileged viewpoint, but no less real for their apparent impossibility. In the year 1006, observers across the globe witnessed a celestial spectacle unlike any seen before, a star suddenly blazing brighter than Venus, casting shadows at midnight and remaining visible even during daylight for weeks. This was supernova 1006, the brightest stellar explosion in recorded history, whose shockwaves still ripple through space at 30,000 kilometers per second, a tenth the speed of light. Modern telescopes reveal these expanding waves as delicate filaments in X-ray light, tracing the aftermath of a detonation so powerful it briefly outshone every other object in the night sky combined. The physics behind this cosmic shockwave begins with a white dwarf stealing material from a companion star until it crosses a critical threshold. The entire star detonates in a thermonuclear fireball, ejecting its outer layers at velocities approaching 6% light speed within minutes. As this debris plows into surrounding interstellar gas, it generates a secondary shockwave that races ahead even faster, a superheated tsunami of ionized particles where electrons spiral around magnetic fields, emitting synchrotron radiation across the electromagnetic spectrum. What medieval astronomers saw as a brilliant new star was actually this shockwave's visible light, while modern X-ray observatories like Chandra capture the far more energetic aftermath invisible to human eyes. Historical records from 1006 read like early scientific documents hidden in poetic descriptions. Chinese astronomers reported a guest star appearing in the constellation Lupus, its light fluctuating over weeks before fading. Egyptian observers noted its brilliance rivaling the moon's crescent, while European monks documented it as a heavenly omen. These accounts prove invaluable today, allowing astronomers to pinpoint the supernova's timing and correlate it with the expanding debris field we now observe. The shockwave's current diameter spans nearly 60 light-years, its faint optical filaments barely visible through telescopes but glowing intensely in X-rays where gas temperatures exceed 50 million degrees. What makes supernova 1006 particularly fascinating is how its shockwave interacts with the interstellar medium. Unlike a smooth ripple, the expanding shell shows intricate knots and streamers where denser gas clouds resist the blast, creating turbulent eddies that accelerate particles to near light speed. Some regions glow predominantly in radio waves, where electrons spiral around magnetic fields, while others shine in high-energy gamma rays produced when cosmic rays collide with gas atoms. This multi-wavelength signature turns the remnant into a natural laboratory for studying particle acceleration on cosmic scales, processes we usually only recreate in kilometer-long particle accelerators on Earth. The shockwave's sheer speed also distorts our view through relativistic effects. Material moving toward us appears brighter and blue-shifted, while receding gas looks dimmer and redshifted, a phenomenon allowing astronomers to map the remnant's three-dimensional structure. Spectroscopic measurements reveal elements forged in the explosion itself: silicon, oxygen, and iron being hurled into space, where they'll eventually mix with interstellar clouds and form future generations of stars and planets. Every atom in our bodies contains stardust from such cataclysms, making supernova remnants like this one both a destructive and creative force in galactic evolution. As the shockwave continues expanding at its blistering pace, it gradually slows while sweeping up more interstellar material. In another few thousand years, it will become indistinguishable from the surrounding gas. But for now, supernova 1006 serves as a breathtaking reminder that the cosmos operates on scales of energy and velocity that dwarf human experience. Its light may have faded centuries ago, but the echoes of that detonation still reverberate through space, carrying secrets about how stars live, die, and seed the universe with the building blocks of everything we know. Streaking through the Milky Way's outskirts at nearly 300 kilometers per second, the Smith Cloud isn't just another wisp of interstellar gas. It's a cosmic bullet the size of 30 million suns, hurtling toward our galaxy with enough momentum to reshape entire star systems. This colossal structure, spanning 11,000 light-years from end to end, moves with such ferocity that it could cross the distance from Earth to the Sun in just 14 hours, leaving a trail of ionized hydrogen glowing faintly in radio wavelengths. But what makes this intergalactic projectile truly baffling isn't its speed alone. It's the growing evidence that this may be a rare intruder from beyond the Milky Way, carrying chemical fingerprints unlike anything in our galactic neighborhood. The mystery begins with the cloud's unusual composition. While most gas clouds in the Milky Way's halo contain heavy elements forged in stellar furnaces, the Smith Cloud shows sulfur and oxygen levels barely one-third what we'd expect, a chemical signature more typical of pristine intergalactic space. This suggests it might have originated in the dwarf galaxies orbiting ours, where star formation and thus heavy element production occurs far less frequently. Like finding a bottle with ancient seawater floating in modern harbor, the cloud's chemistry hints at origins untouched by the pollution of countless supernova that have enriched our galaxy's gas over billions of years. Yet the plot thickens when we examine the cloud's trajectory. Sophisticated radio telescope observations reveal it's not just falling toward the Milky Way, it's on a boomerang path. Approximately 70 million years ago, this gargantuan gas structure made its first known pass through our galactic disk, creating shock waves that still ripple through nearby star-forming regions. The encounter stripped away much of its original mass, leaving the tattered remnant we see today, now arcing back for another collision in about 30 million years. When it strikes, the impact will likely trigger fireworks of new star formation, compressing galactic gas like a snowplow piling up drifts, except here, the snow will ignite as brilliant young stars. The most startling revelation comes from the cloud's magnetic wake. As it plows through the Milky Way's magnetized halo at supersonic speeds, the Smith Cloud trails twisted magnetic fields detectable through polarized radio emissions. These distortions act like cosmic breadcrumbs, tracing not just where the cloud has been, but how the galaxy's invisible magnetic scaffolding interacts with high-velocity intruders. The turbulence generated in its wake creates conditions similar to those in the early universe, allowing astronomers to study how primordial gas might have behaved as it fell into budding galaxies billions of years ago. Current theories suggest this hypervelocity cloud might be the visible tip of a much larger phenomenon. Some models propose its trailing dark matter, an invisible gravitational anchor that helped it survive its first passage through the Milky Way's dense disk. If true, tracking its motion could provide rare clues about dark matter's distribution in our galactic suburbs. Other simulations show similar clouds might be the shredded remains of dwarf galaxies torn apart by tidal forces, their stars scattered too faint to detect while their gas lingers as ghostly, high-speed debris. What awaits the Smith Cloud ultimately depends on its still unknown mass. If it carries enough hydrogen, its next collision with the Milky Way could birth dazzling stellar nurseries visible from neighboring galaxies. Too little, and it may dissipate like fog burning off under morning sunlight, its atoms quietly joining the galaxy's interstellar reserves. Either way, this cosmic speedster serves as a reminder that even our island universe isn't isolated. It's constantly exchanging matter with its surroundings in a dynamic, high-velocity dance that shapes galactic evolution over eons. SDSS J0927 plus 2943 isn't just another dead star, it's a cosmic catapult survivor hurtling through the void at 2,400 kilometers per second, fast enough to cross the continental United States in less than 2 seconds. This white dwarf, the crushed core of a once normal star, moves with such reckless velocity that it's not merely escaping its home galaxy, it's punching through intergalactic space like a bullet through smoke, leaving a faint ionized trail that betrays its extraordinary past. The energy propelling it rivals the output of 100 supernovas combined, suggesting this stellar corpse was launched by one of the universe's most violent and lopsided explosions. The clue to its origin lies in the imbalance of its ejection. When most stars die, their supernova explosions distribute energy relatively evenly, leaving behind neutron stars or black holes with modest kicks. But as DSS J0927 plus 2943 tells a different story, spectroscopic analysis reveals its composition matches material typically found deep within a star's core, suggesting it was violently ejected before completing the full supernova process. The prevailing theory paints a dramatic scene, a binary system where one star exploded so asymmetrically that the surviving white dwarf got shot out like a champagne cork from a shaken bottle, propelled by the sheer force of uneven detonation. Tracking this rogue star's path leads to even more intrigue. Its trajectory points back to no obvious galactic origin, implying it's been traveling for hundreds of millions of years, long enough to have crossed multiple galaxies if they happen to lie in its path. The kinetic energy it carries is mind-boggling. A single second of its motion could power human civilization at current levels for over 300 years. Yet despite this blistering speed, space is so vast that even at 2,400 kilometers per second, its movement against background galaxies appears glacial through telescopes. What makes this white dwarf particularly fascinating is how it challenges our understanding of stellar deaths. Typical supernova models struggle to explain how any object could be accelerated to such extremes without being torn apart. Some theorists propose exotic scenarios involving intermediate mass black holes or rare triple-star system breakups as potential launch mechanisms. Others suggest the star might have been orbiting close to a supermassive black hole when its companion exploded, adding gravitational slingshot effects to the explosive kick, a cosmic double whammy of acceleration. The observational evidence provides tantalizing clues about its journey. The white dwarf's outer layers show unusual stripping patterns, consistent with plowing through intergalactic gas at hypersonic speeds. Imagine stellar windburn on an unimaginable scale. Its spectral lines also reveal a curious lack of certain heavy elements, suggesting it originated in a galactic region with distinct chemical signatures from our cosmic neighborhood. Like analyzing the wear patterns on a bullet to reconstruct the gun that fired it, astronomers use these subtle signatures to piece together the cataclysmic events that created such an extraordinary celestial projectile. As SDSS J0927 plus 2943 continues its lonely voyage, it serves as a natural probe of the sparsely populated intergalactic medium. The faint shockwave preceding it interacts with tenuous gas filaments between galaxies, creating ultraviolet bow shocks detectable by sensitive space telescopes. These interactions provide rare data about the mysterious warm-hot intergalactic medium, a diffuse web of gas that may contain half the universe's normal matter, but remains notoriously difficult to study. Every light year this stellar fugitive travels yields new information about the spaces between galaxies that conventional astronomy usually overlooks. This cosmic speed demon also raises profound questions about how many similar objects might be racing unseen through the darkness. Current estimates suggest our galaxy alone could have ejected thousands of hypervelocity stars over its lifetime, most now lost in intergalactic space. Future telescopes like the Vera Rubin Observatory may uncover more of these extreme travelers, each carrying unique stories about the violent processes that shaped our universe. For now, SDSS J0927 plus 2943 stands as a stark reminder that even in death, stars can achieve velocities that push the boundaries of physics itself, transforming from quiet stellar embers into the fastest unbound objects known to science. Amid the swirling dust of stellar nurseries, newborn stars unleash some of the most spectacular tantrums in the universe, blistering jets of plasma that rip through space at 700 kilometers per second. Herbig-Haro objects like HH34 serve as nature's neon signs, marking where these hypersonic outflows slam into surrounding gas at speeds that would cross Earth's diameter in 18 seconds. Hubble's iconic images reveal these jets stretching light years into space, their glowing tendrils twisting like celestial fireworks frozen in mid-explosion. The violence begins deep within the star's formation process. As a protostar gathers material from its surrounding disk, powerful magnetic fields channel some of that infalling gas away from the poles at blistering speeds. These narrow beams become ionized by the young star's intense radiation, transforming into the glowing plasma streams we observe. What makes HH34 particularly striking is its multiple shock fronts visible as knotted beads along the jet's length, where faster-moving material plows into slower ejecta, creating standing waves of superheated gas. Each collision heats the plasma to tens of thousands of degrees, making it shine across the electromagnetic spectrum. Hubble's time-lapse observations reveal these jets aren't steady flows but episodic outbursts. Clumps of material erupt every few decades, creating cascading shock waves that travel down the jet like cosmic sound waves. The newest knots near the star move fastest, sometimes showing proper motion equivalent to covering the moon's diameter every 20 years, a snail's pace across the sky, but representing actual velocities that would vaporize any known material instantly. As these bullets of plasma travel outward, they sweep up surrounding nebular material, sculpting intricate cavities that resemble underwater corals blown up to interstellar scales. The colors in Hubble's images tell a deeper story. Blue regions mark the hottest, most energetic gas near the jet's core, while red filaments trace cooler material being dragged along in the outflow's wake. Spectroscopy reveals abundant iron, silicon, and oxygen in these flows, elements that were locked in dust grains until the jet shockwaves vaporized them. This constant enrichment of surrounding nebulae with heavy elements demonstrates how even the youngest stars participate in the galactic recycling program, dispersing materials that will eventually form new generations of stars and planets. What makes HH34's jets particularly valuable for astronomers is their relative proximity, about 1,500 light-years away, allowing detailed study of structures as small as our solar system. Infrared observations peer through the dust to show how the jets originate very close to the protostar, within a region no larger than Pluto's orbit. Here, magnetic fields twist into helical shapes, acting like particle accelerator coils to focus and launch the plasma streams. Radio telescope data complement Hubble's optical views, revealing colder molecular gas entrained in the outflow that doesn't glow visibly but plays a crucial role in shaping the surrounding nebula. These stellar jets aren't just beautiful accidents, they're fundamental to star formation itself. By carrying away excess angular momentum, they allow the protostar to continue accreting material that would otherwise spin too fast to fall inward. Without this release valve, stars might never grow beyond tiny embryonic cores. HH-34's spectacular display gives us front-row seats to this balancing act between gravity and rotation, showing how nature solves complex physics problems with breathtaking precision and beauty. Every glowing knot in its jet represents another step in the star's growth process, a cosmic progress bar counting down the millions of years until this tantrum-throwing infant settles into stable adulthood. Meet 2 mass J0348-6022, the fastest spinning brown dwarf ever discovered, a cosmic overachiever that defies its failed star, labeled by whirling at speeds that would rip ordinary planets to shreds. This celestial speed demon completes a full rotation every 1.1 hours, its equator racing through space at 100 kilometers per second, fast enough to cross Earth's diameter in under 7 minutes. At that velocity, if this brown dwarf were a car tire, it would spin 3,000 times faster than a Formula One racer's wheels at top speed. Yet despite spinning 20 times faster than Jupiter, it holds itself together through a combination of extreme density and mysterious internal forces we're only beginning to understand. What makes this rapid rotation even more astonishing is 2 mass J0348-6022's peculiar nature. Brown dwarfs occupy the strange twilight between planets and stars, too massive to be planets, yet too small to sustain hydrogen fusion like true stars. This particular specimen packs about 75 Jupiter masses into a sphere only 20% larger than Jupiter itself, meaning its material endures pressures 1,000 times greater than Earth's core. That incredible density provides the gravitational muscle to counteract centrifugal forces that would fling a less compact object apart. Imagine trying to spin a water balloon rapidly versus a bowling ball. The latter's tight mass distribution resists deformation even at high speeds, much like this brown dwarf's ultra-dense interior. Scientists discovered this rotational record breaker through subtle changes in its infrared brightness. As dusty atmospheric features whirl in and out of view during each breakneck rotation, they create predictable brightness fluctuations like cosmic lighthouse beams sweeping past Earth every 66 minutes. Spectral measurements reveal another clue to its stability, an unexpectedly strong magnetic field, roughly 200 times more powerful than Jupiter's. This magnetic grip may act like an invisible skeleton, helping to bind the brown dwarf's atmosphere against catastrophic dispersal. The field generates dazzling auroras near its poles, where charged particles spiral along magnetic lines and collide with atmospheric gases, creating otherworldly northern lights visible across light years. The real mystery lies in how 2 mass J0348-6022 attained such extreme spin in the first place. Most brown dwarfs slow down over billions of years as their magnetic fields interact with stellar winds and accretion disks. This one might have avoided the breaks through an unusual youth, perhaps forming from the violent merger of 2 smaller brown dwarfs, combining their angular momentum like a cosmic figure skater pulling in both arms while spinning. Alternatively, it could still be recovering from a recent gravitational encounter that torqued it up to these dizzying speeds. Whatever the cause, its current velocity pushes the theoretical limits for brown dwarf rotation, providing astrophysicists with a natural laboratory to study how such objects evolve under extreme conditions. Surprisingly, this brown dwarf's rapid spin might actually help explain why it hasn't torn itself apart. Rotation at this speed creates an equatorial bulge, redistributing mass toward the outer layers and effectively lowering the central pressure. This self-regulating mechanism prevents the core from reaching critical densities that could trigger destabilizing nuclear reactions. A safeguard that keeps 2 mass J0348-6022 in a stable, if frenetic, equilibrium. The same principle applies to neutron stars, where extreme rotation actually prevents gravitational collapse into black holes. Here, scaled down to brown dwarf proportions, we see nature's universal physics playing out across vastly different cosmic objects. Future observations aim to probe deeper into this exotic rotator's secrets. The James Webb Space Telescope could detect atmospheric variations across its surface, mapping storm systems larger than continents that whip around at hypersonic speeds. Radio telescopes might catch bursts of cyclotron radiation from electrons spiraling in its powerful magnetic field, revealing how charged particles behave in such extreme environments. Each new finding adds to our understanding of these borderline celestial objects, neither true stars nor planets, but captivating worlds that stretch the definitions of both. 2 Mass J0348-6022 stands as a cosmic curiosity, challenging our assumptions about rotational limits while showcasing the universe's flair for creating exceptions to every rule. When a black hole tears apart a passing star, it doesn't just create a spectacular light show. It becomes nature's ultimate particle accelerator. Tidal disruption events unleash some of the most violent outflows in the universe, where stellar debris doesn't just fall inward, it gets catapulted outward in relativistic jets moving at 90% the speed of light. Picture this: an unlucky star wanders too close to a supermassive black hole's event horizon, where gravitational forces stretch it like taffy until it snaps apart in a process called spaghettification. While most of the star's material forms a swirling accretion disk, simulations reveal that up to 20% gets flung away at velocities approaching physics' ultimate speed limit. These hypervelocity outflows aren't random splashes, they're precision engineered by some of the most extreme physics in the cosmos. As magnetic fields in the newly formed accretion disk twist into helical coils, they launch bipolar jets along the black hole's rotation axis like cosmic railguns. The process mirrors how quasars produce their jets, but compressed into an explosive timescale of weeks rather than millennia. One particularly well-studied event, Assassin 14 Li, showed X-ray evidence of iron atoms racing outward at 30% light speed, so fast their spectral lines shifted visibly toward the red end of the spectrum. Later observations revealed even faster material in the jet's core, where particles surfed shockwaves at 90% light speed, their kinetic energy output briefly rivaling the luminosity of an entire galaxy. What makes these relativistic outflows so scientifically precious is their fleeting nature. Unlike persistent quasar jets that shine for millions of years, tidal disruption jets last mere months before fading, giving astronomers a rare opportunity to study how such extreme particle acceleration initiates and evolves. The 2019 event at 2019 DSG provided a breakthrough when radio telescopes detected synchrotron radiation from electrons spiraling along magnetic field lines in the outflow. By tracking how this emission brightened and dimmed, scientists reconstructed the jet's internal structure like medical imaging scans, revealing nested layers where velocity increased progressively toward a narrow, ultra-fast core. These observations confirmed theoretical models suggesting the jets act like cosmic sorting machines, with slower moving material forming a protective sheath that collimates and stabilizes the inner relativistic beam. The most violent tidal disruptions generate light echoes that serve as natural tomography scans of the surrounding interstellar medium. When jetted material slams into pre-existing gas clouds at near light speed, it creates shock fronts that glow across the electromagnetic spectrum. In 2022, researchers studying the event J2150 detected telltale X-ray flickers from these collisions, each pulse encoding information about both the jet's contents and the distant gas clouds it was plowing through. This accidental sonar technique revealed interstellar gas filaments 10,000 light-years from the black hole that would otherwise remain invisible, proving these cataclysms can illuminate the universe's hidden scaffolding. But perhaps the most mind-bending implication lies in what these outflows carry away. Recent simulations suggest tidal disruption jets might transport heavy elements like gold and uranium forged in the star's final moments, seeding distant space with cosmic riches at velocities that could cross entire galaxy clusters in just millions of years. When the next generation of gravitational wave detectors comes online, they may even catch the subtle space-time ripples from the black hole's recoil as it launches these asymmetrical jets, a smoking gun signature that would reveal exactly how much momentum gets transferred during these violent stellar feasts. Until then, each new tidal disruption event offers fresh insights into how black holes, often seen as cosmic vacuum cleaners, can also become the universe's most powerful slingshots. While the Milky Way may seem like a stationary home against the night sky, our galaxy is actually racing through the cosmos at an astonishing 630 kilometers per second, fast enough to travel from Earth to the Moon in just 10 minutes. This staggering velocity isn't random. The entire Milky Way, along with our neighboring galaxies, is being pulled toward a gravitational heavyweight called the Shapley supercluster, a dense knot of galaxies 700 million light-years away containing the mass of over 10,000 Milky Ways. But here's where it gets truly fascinating. We only know this motion exists because of an ancient glow permeating the universe, the cosmic microwave background radiation. This faint afterglow from the Big Bang serves as the universe's ultimate reference frame. Just as raindrops appear to streak diagonally across a speeding car's windshield, the microwave background shows a dipole anisotropy, a slight temperature variation caused by our movement through space. The side we're approaching appears slightly warmer as the microwaves get compressed, while the direction we're fleeing from appears cooler as the light stretches. This cosmic Doppler effect reveals not just our speed, but our exact trajectory relative to the universe's primordial light. Without this celestial speedometer, we'd have no way to measure our true motion through the cosmos. The Shapley supercluster's pull tells a deeper story about the universe's hidden architecture. While visible matter can explain some of our galaxy's motion, the full velocity suggests vast amounts of invisible dark matter are also tugging at us from the cosmic web's densest junctions. Current models suggest the Great Attractor, a closer concentration of galaxies, acts as a waypoint in this journey. But Shapley's immense distance proves structures on scales we're only beginning to map wield gravitational influence across mind-boggling distances. Imagine throwing a stone into a pond and watching ripples interact, except here, the pond is space-time itself, and the ripples have been expanding for billions of years. What makes this motion particularly humbling is how it upends our sense of cosmic centrality. The Sun's orbit around the Milky Way's core, Earth's path around the Sun, and our solar system's bobbing motion through the galactic plane all become minor wobbles compared to this galaxy-wide rush toward Shapley. Even as you sit still, you're being carried along at over 2 million miles per hour by forces that began gathering momentum when the universe was half its current age. This grand migration won't culminate in any dramatic collision. The expansion of space ensures we'll never actually reach the Shapley supercluster, but it serves as a constant reminder that in an ever-moving universe, nothing truly stands still. The cosmic microwave background continues to refine our understanding of this motion. Recent measurements from the Planck satellite narrowed our speed to within 1 kilometer per second precision, while also revealing subtle flows of galaxies moving in concert on scales of hundreds of millions of light-years. These coordinated motions hint at even larger structures beyond Shapley, perhaps the Vela supercluster recently mapped behind the Milky Way's dusty disk, whose gravity may be contributing to our journey. Each new observation peels back another layer of the cosmic onion, showing us that what we once called the universe is really just our local neighborhood in a far vaster and more dynamic cosmos than we ever imagined. Far from being a passive island universe, the Milky Way is an eager participant in the cosmic dance, drawn toward the densest concentrations of matter by the same gravitational rules that make apples fall from trees. That this motion leaves detectable imprints in relic radiation from the universe's infancy connects us directly to the Big Bang itself, a thread of cause and effect stretching across 13.8 billion years, written in the subtle warping of microwaves and the silent rush of galaxies toward their invisible masters. The next time you look up at the seemingly fixed stars, remember they're all moving together in a grand voyage whose ultimate destination remains written in the invisible gravitational language of the cosmos. Deep in the constellation Puppies, two cosmic corpses perform a deadly dance at unfathomable speeds. Pulsar J0737-3039, the fastest known binary pulsar system in the universe. These neutron stars, each more massive than our Sun yet barely 20 kilometers across, whip around each other at 1 million kilometers per hour, completing each frantic orbital ballet in just 2.4 hours. Their motion is so extreme that from the surface of one pulsar, the other would appear to streak across the sky in minutes, its crushing gravitational pull warping space-time with each pass. What makes this system truly extraordinary isn't just its velocity, it's the precision with which we can predict its cataclysmic future. General relativity calculations show these pulsars spiraling inexorably toward each other, losing orbital energy through gravitational waves at a rate matching Einstein's equations to within 0.0003% accuracy. Every revolution brings them 1.6 millimeters closer, a microscopic distance by cosmic standards, but one that ensures their inevitable collision in approximately 85 million years. When that final moment comes, the merger will unleash more energy in gravitational waves than all the stars in the observable universe emit as light during the same time frame. The pulsar's discovery in 2003 revolutionized astrophysics by providing the first double pulsar system. Both neutron stars beam detectable radio pulses toward Earth like hyperactive cosmic lighthouses. This rare configuration allows scientists to measure relativistic effects with unprecedented precision. As the pulsars orbit, their pulses arrive at Earth with subtly shifting timing, distorted by phenomena like Shapiro delay, where signals slow when passing through curved spacetime near each neutron star, and geodetic precession, a wobble in their spin axes caused by relativistic frame dragging. These minute variations serve as a natural laboratory for testing gravity's nature under conditions impossible to recreate on Earth. One particularly fascinating quirk of this system involves Pulsar B, the slower spinning companion that mysteriously stopped pulsing in 2008. Scientists believe its magnetic field, weakened by the senior pulsar's relentless particle wind, could no longer generate detectable beams, yet this apparent silencing proved just as valuable for science, allowing researchers to study how pulsar winds shape their environments by observing the still pulsing partner's influence on its now quiet twin. The system's evolving dynamics offer a real-time view of binary star evolution's final chapters, showcasing how even the densest objects in the universe can't escape relativity's relentless influence. The impending collision carries profound implications beyond just another spectacular cosmic fireworks show. When these pulsars finally merge, they'll likely form a black hole while briefly creating the strongest magnetic fields known to exist, potentially a quadrillion times more powerful than Earth's protective magnetosphere. The event could solve long-standing mysteries about the origin of heavy elements like gold and platinum, which current models suggest might form in the neutron-rich debris ejected during such mergers. Future gravitational wave detectors might catch the merger's final milliseconds, revealing details about neutron star interiors that even the most advanced particle colliders can't probe. For now, Pulsar J0737-3039 continues its measured death spiral, each rotation ticking down toward an apocalypse that will ripple across the cosmos. Its existence reminds us that even the most violent cosmic events operate with clockwork precision, governed by physical laws we're only beginning to fully comprehend. Every pulse from these dancing stellar ghosts carries encrypted messages about spacetime's true nature, a cosmic countdown written in gravity's own language. At the heart of certain galaxies, black holes don't just consume matter, they spit it back out with unimaginable fury. PDS 456, a brilliant quasar 500 million light-years away, generates cosmic hurricanes so powerful they reshape entire galaxies, launching superheated gas at 90,000 kilometers per second, a staggering 30% the speed of light. These aren't gentle breezes, but hypersonic tsunamis of ionized particles carrying enough energy to blow star-forming gas clean out of their host galaxies, effectively shutting down stellar production for eons. The engine behind these ultra-fast outflows lies in the chaotic maelstrom surrounding the supermassive black hole. As matter spirals inward through the accretion disk, intense radiation pressure from the searing hot gas creates a feedback loop. Photons smash into atoms with such force that they push material outward rather than letting it fall into oblivion. Magnets play a crucial role too, with magnetic field lines twisting like cosmic spaghetti to funnel some of this material into focused streams. The result is a bipolar hurricane stretching tens of thousands of light years, where elements like iron get swept up in the flow and detected through their telltale X-ray signatures millions of years later. What makes PDS 456 outflow particularly astonishing is its sheer scale. Observations from the European Space Agency's XMM Newton telescope revealed the wind spans a region larger than our entire solar system, carrying enough kinetic energy to power the Milky Way for 10,000 years. The wind's broad absorption lines in X-ray spectra show it isn't uniform, like a storm with varying wind speeds. It contains multiple velocity components from different regions of the outflow. Some inner portions reach those record-breaking 30% light speeds, while outer streams move at a comparatively sluggish 10,000 kilometers per second, still fast enough to cross Earth's diameter in under 2 seconds. These outflows solve a long-standing cosmic mystery: why there aren't more extremely massive galaxies in the universe. Without some mechanism to halt star formation, galaxies should theoretically grow indefinitely as they absorb gas from intergalactic space. Ultra-fast winds provide that regulatory break by ejecting star-forming material at velocities too great for gravity to recapture. They essentially starve their host galaxies of future stellar fuel. In PDS 456 case, the outflow removes the equivalent of 5 suns worth of material every year, enough to build a star cluster like the Pleiades every few millennia. The dynamics of these winds reveal even wilder physics when examined closely. As the outflow rams into slower-moving interstellar gas, it creates shock fronts where particles get accelerated to near light speed, nature's own version of a particle collider, but operating on galactic scales. Some models suggest these interactions might generate the mysterious ultra-high-energy cosmic rays that occasionally bombard Earth's atmosphere. The winds also carry heavy elements forged in supernova and stellar cores far beyond their birthplace, seeding intergalactic space with the building blocks for future generations of stars and planets. PDS 456 isn't unique. Astronomers have catalogued dozens of similar systems, each offering variations on this extraordinary theme. What sets it apart is how clearly we can observe the outflow's structure across multiple wavelengths. Radio telescopes trace the wind's interaction with surrounding dust, while infrared observations reveal how dust grains absorb and re-radiate the quasar's intense light. Future instruments like the James Webb Space Telescope promise to dissect these outflows in even greater detail, potentially revealing how they evolve over cosmic time and influence large-scale galaxy formation. These black hole-powered winds represent one of the most dramatic examples of cosmic feedback, a process where the energy output from one astrophysical phenomenon regulates another. They showcase black holes not just as destructive monsters, but as sculptors of galactic architecture, shaping the evolution of their surroundings with the same gravitational dominance that once made them seem like unstoppable cosmic vacuum cleaners. Far from being passive consumers of matter, supermassive black holes like the one in PDS 456 demonstrate how the most violent forces in nature can paradoxically create order and structure on the grandest scales imaginable. While cosmic objects routinely reach velocities that defy imagination, humanity has its own speed champion, the Parker Solar Probe, currently the fastest human-made object ever built. Hurtling through space at 700,000 kilometers per hour, this daring spacecraft would cross the continental United States in under 20 seconds. At this blistering pace, it could theoretically reach the moon in under 36 minutes, a journey that typically takes spacecraft several days. Yet for all its impressive velocity, the Parker Solar Probe's speed represents just 0.064% of light speed, a humbling reminder of how far our technology still lags behind nature's most extreme cosmic accelerators. What makes this spacecraft's speed particularly remarkable isn't just the number, it's how it achieves such velocity. Rather than relying solely on powerful rocket launches, the probe uses Venus's gravity as a cosmic slingshot, gradually tightening its orbit around the Sun with each pass. During its closest solar approaches, the spacecraft dives mere 6 million kilometers above the Sun's searing surface, closer than any human-made object has ever ventured, where temperatures reach 2,500 degrees Fahrenheit. The probe's carbon composite heat shield, just 4.5 inches thick, withstands conditions that would vaporize conventional spacecraft, allowing its instruments to sample the solar wind where it's born. These suicidal dives into the Sun's corona are precisely what give the Parker Solar Probe its record-breaking speed. As the spacecraft falls toward our star, the Sun's immense gravity accelerates it like a stone dropped from space, reaching velocities that temporarily make it the fastest-moving human-made object in history. The physics mirrors how comets gain speed during their close solar passes, except here the trajectory is carefully controlled to survive multiple encounters. Each perihelion, the closest point in its orbit, delivers fresh data about solar phenomena that have puzzled scientists for decades, from the mystery of why the corona is millions of degrees hotter than the Sun's surface to the mechanisms that launch charged particles across the solar system as solar wind. The contrast between the Parker Solar Probe's speed and cosmic velocities puts our place in the universe in perspective. While 700,000 kilometers per hour seems unimaginably fast to us, it's still 20,000 times slower than hypervelocity stars ejected from galaxies, and nearly 200,000 times slower than particles in quasar jets. Yet this mission represents humanity's most determined effort to touch the Sun, literally racing through an environment where forces we barely understand dominate. The probe's velocity allows it to keep up with the Sun's rotation momentarily, giving its instruments unprecedented time to study how magnetic fields and plasma interact in the birthplace of space weather. Future projections suggest the probe will keep breaking its own records. Its final orbits in 2025 will bring it even closer to the Sun, just 6 million kilometers from its surface, where it could potentially reach speeds approaching 750,000 kilometers per hour. This gradual acceleration mirrors how cosmic objects gain velocity through repeated gravitational assists, demonstrating that whether human-made or natural, the laws of physics provide the same tools for achieving extreme speeds. The Parker Solar Probe's daredevil maneuvers not only expand our understanding of the star that gives us life, they prove that with clever physics and engineering, humanity can momentarily join the universe's speed elite. The early universe didn't just move fast, it rewrote the rulebook on cosmic speed limits entirely. During the brief but mind-bending period of inflation, mere fractions of a second after the Big Bang, space itself expanded at rates that would make even light seem sluggish. Picture this: regions of the universe that could once exchange photons suddenly found themselves separated by distances growing faster than light could bridge them. This wasn't objects moving through space faster than light, a forbidden scenario in Einstein's relativity, but space itself stretching at velocities that would leave photons in the dust. Today, we see echoes of this extreme motion in the most distant quasars, their light stretched into infrared oblivion by cosmic expansion. The current record holder, Euler's J 1342 plus 0.928, races away from us at 94% light speed, not because the quasar itself is moving, but because the space between us is growing at a staggering rate. Its ultraviolet emissions, energetic enough to ionize atoms when they left 13 billion years ago, arrive at our telescopes as feeble infrared whispers, having been stretched across an expanding universe like taffy pulled to breaking point. What makes this cosmic recession truly bizarre is how it plays with causality itself. Quasars like J 1342 plus 0.928 now reside so far beyond our cosmic horizon that no signal we send could ever reach them, nor could any future telescope observe what they've become. Their light reaching us today shows them as they were when the universe was just 690 million years old, forever frozen in our view as infant galaxies, their present-day forms racing away at speeds that render them fundamentally unknowable. The expansion of space has effectively erased them from our future light cone, leaving only these faded postcards from the universe's childhood. Inflation's brief superluminal expansion solved cosmic puzzles no other theory could touch. It explains why opposite sides of the observable universe share nearly identical temperatures despite never having had time to thermally equilibrate. They were once neighbors before inflation stretched them apart. This period of exponential growth also amplified quantum fluctuations into the density variations that later seeded galaxies and galaxy clusters. The same physics that once propelled space to expand faster than light now manifests in those distant quasars' redshifted light, carrying encoded information about the universe's most extreme growth spurt. The most fascinating aspect lies in how these distant quasars will eventually disappear from view. As their recession velocities approach light speed due to accelerating cosmic expansion, their light will redshift into undetectability, first slipping beyond the reach of optical telescopes, then vanishing from infrared detectors, and finally becoming nothing more than faint ripples in the cosmic microwave background. This gradual cosmic fade-out serves as a reminder that the universe's history isn't permanently accessible. Some chapters are being erased by the relentless expansion of space itself, their protagonists carried beyond the boundaries of observation by velocities no spacecraft could ever hope to match. Yet for now, these incredibly distant quasars remain our best windows into the universe's most extreme motions, both the brief superluminal expansion of inflation and the inexorable cosmic acceleration that continues today. Each photon we detect from them has fought against the expanding universe for billions of years, carrying stories from an era when the cosmos was fundamentally different. Their extreme redshifts don't just represent velocity, they're cosmic time capsules, preserving the moment when the universe transitioned from opaque plasma to transparent space and began the long journey toward the structured cosmos we inhabit today. The Bullet Cluster isn't just another galactic collision. It's a cosmic crime scene where dark matter has been caught fleeing the scene at nearly 5,000 kilometers per second. This pair of merging galaxy clusters, officially known as 1E0657-558, demonstrates one of the most violent large-scale motions ever observed, with X-ray telescopes revealing a breathtaking separation between visible gas and the invisible gravitational scaffolding that holds galaxies together. The numbers alone are staggering. The cluster's gas clouds, heated to 100 million degrees by the impact, lag behind the bulk of the mass like cosmic exhaust, while the galaxies and their dark matter counterparts continue racing ahead at speeds that could cross the entire Milky Way in just 200,000 years. What makes this collision so scientifically revolutionary is how it provides the first direct evidence for dark matter's existence. As the clusters plowed through each other, their interstellar gas, the only part of the system we can see directly in X-rays, slammed together with such force that it slowed dramatically, like two cups of water thrown at each other in midair. Meanwhile, the galaxies themselves, along with their accompanying dark matter halos, barely noticed the collision, passing through each other almost unaffected because dark matter interacts only through gravity, not electromagnetic forces. The result, a visible rift between the hot gas glow and the gravitational lensing effects, marking where most of the mass actually resides, proof that something invisible but massive is steering the cosmic dance. The mechanics behind this high-speed merger read like a physics textbook come to life. Simulations suggest the bullet cluster's galaxies are moving too fast to have been accelerated by visible matter alone. Their velocity implies the presence of a hidden gravitational anchor, likely the dense dark matter structures preceding each cluster. As they collided, this dark matter created gravitational lenses that distort background galaxies' light, allowing astronomers to map its distribution with precision. The gas, slowed by electromagnetic interactions, now trails behind like a cosmic wake, its turbulent swirls captured in exquisite detail by the Chandra X-ray Observatory. These observations don't just confirm dark matter's existence, they reveal how it behaves during the universe's most energetic events. Beyond proving dark matter's reality, the bullet cluster also showcases the sheer violence of galactic collisions. The kinetic energy released dwarfs anything in our solar system, equivalent to millions of gamma-ray bursts detonating simultaneously. Yet despite this chaos, the cluster's stars rarely collide due to the vast empty spaces between them, a reminder that even the universe's fastest impacts often play out as ghostly encounters rather than catastrophic crashes. The gas, however, tells a different story. Its shock waves compress and heat it until it glows in X-rays, creating the bullet shape that gives the cluster its nickname, a spearhead of plasma stretching 2 million light-years across space. This collision isn't just a spectacle, it's a time machine. The event likely began around 150 million years ago, and we're witnessing a snapshot of a process that will take billions of years to complete. Future telescopes may catch similar systems at different stages, helping astronomers piece together how dark matter guides galaxy cluster evolution across cosmic time. For now, the bullet cluster remains one of the most compelling pieces of evidence that we're surrounded by an invisible cosmic architecture, a hidden framework moving at speeds that reshape our understanding of mass, gravity, and the very fabric of the universe itself. What if the universe's ultimate speed limit wasn't actually a limit at all? Beyond the hypervelocity stars and relativistic jets we've explored, theoretical physics offers glimpses of even more extreme possibilities: particles that could outpace light itself and warp drives that might bend spacetime to our will. Enter tachyons, the hypothetical particles that don't just approach light speed but live permanently beyond it, zipping through the cosmos at velocities that make photons look sluggish. Unlike ordinary matter that requires infinite energy to reach light speed, tachyons would theoretically possess imaginary mass, a concept straight from advanced quantum field theory, allowing them to exist only at faster than light velocities. Imagine a cosmic speedster born in fast forward, where time itself might flow backward from its perspective, creating causality paradoxes that still give physicists headaches. The Alcubierre drive takes a radically different approach to breaking the cosmic speed limit. Instead of moving through space faster than light, this theoretical concept, first proposed by physicist Miguel Alcubierre in 1994, suggests warping spacetime itself. Picture a starship sitting inside a bubble of compressed space in front and expanded space behind, surfing a wave of distorted geometry while never locally exceeding light speed. The mathematics resembles how the universe expanded faster than light during inflation, just on a controllable scale. While the energy requirements appear prohibitive, some calculations suggest needing the mass energy of Jupiter. Recent refinements propose negative energy densities that might make the concept marginally less impossible. Both ideas, tachyons and warp drives, represent humanity's refusal to accept light speed as the final frontier, even if current physics places them firmly in the realm of speculation. The implications of faster-than-light travel or communication would rewrite cosmic rulebooks. Tachyonic telephone calls could theoretically arrive before they're placed, violating causality in ways that challenge our fundamental understanding of time. Alcubierre warp bubbles might generate deadly Hawking radiation at their boundaries, frying any passengers inside. Even more unsettling are the potential time dilation effects. A warp-driven spaceship arriving at Alpha Centauri might find centuries have passed on Earth despite subjective weeks of travel. These paradoxes aren't just plot holes for science fiction. They're serious mathematical consequences that make many physicists skeptical about FTL possibilities. The very fabric of relativity, tested with exquisite precision in everything from GPS satellites to particle accelerators, suggests the universe enforces light speed as the ultimate traffic law for good reason. Yet the pursuit of these ideas continues to drive scientific progress. Experiments have searched for tachyon signatures in high-energy particle collisions and cosmic ray showers, while NASA Eagleworks Lab has conducted benchtop tests of microscale warp field interferometers. Negative energy densities, though exotic, find shadows of possibility in quantum phenomena like the Casimir effect, where parallel plates in a vacuum experience attractive forces from virtual particles. Theoretical breakthroughs in string theory and quantum gravity occasionally revive interest in FTL mechanisms, though always with heavy caveats about energy requirements or stability. What makes these thought experiments valuable isn't their immediate practicality, but how they stress-test our understanding of physics' deepest principles. Perhaps the most profound lesson from these theoretical speed demons is how they reveal the universe's hidden architecture. The fact that relativity permits warp-drive solutions, however impractical, hints at spacetime's flexible nature, while tachyon theories illuminate the delicate balance between causality and quantum mechanics. Even if we never break the light barrier, the mere possibility pushes us to ask better questions about dark energies, accelerating expansion, or quantum entanglements, spooky action at a distance. In this sense, the cosmic speed limit isn't just a wall, it's a mirror, reflecting back all the ways our universe could have been different, and all the reasons it stubbornly remains exactly as we find it. From neutron stars spinning faster than kitchen blenders to hypervelocity stars flung across galaxies like cosmic bullets, the universe operates on speed scales that defy human intuition. We've witnessed pulsars whipping around 700 times per second, their surfaces moving at a quarter light speed, while supermassive black holes like PDS 456 blast matter outward at 30% light speed velocities so extreme they reshape entire galaxies. These aren't just record-breaking oddities, they're fundamental forces sculpting cosmic evolution. Hypervelocity stars seed intergalactic space with heavy elements. Quasars' relativistic jets distribute energy across billions of light years, and even dark matter, revealed in collisions like the Bullet Cluster, moves with silent, invisible power that structures the visible universe. Consider how these extreme speeds create the conditions for life itself. The gold in your jewelry was forged in neutron star collisions moving at relativistic velocities, while the calcium in your bones originated in supernova whose shockwaves accelerate particles to near light speed. The very atoms comprising our bodies were distributed across galaxies by these cosmic speed demons, proving that the universe's fastest phenomena aren't distant curiosities, they're active participants in our existence. Even Earth's motion through space, caught in the Milky Way's 600 km/s rush toward the Shapley supercluster, connects us to the grand gravitational currents flowing through the cosmos. Yet for all we've discovered, the universe undoubtedly holds faster, stranger speedsters waiting to be found. Perhaps undiscovered particles exceed light speed through higher dimensions, or primordial black holes zip through space with velocities dwarfing anything we've measured. Maybe dark energy's accelerating expansion hints at speeds beyond our current physics. As telescopes probe deeper and detectors grow more sensitive, each discovery pushes velocity's boundaries further, revealing a cosmos where the only true limit is our imagination. Now we'd love to hear your thoughts. What cosmic speedster amazed you most? Was it the runaway star S5 HVS1 escaping our galaxy forever? Or the mind-bending space-time warps around Jubris 1915 plus 105 spinning black hole? Share your favorites in the comments and keep looking upward, because in this universe of extremes, tomorrow's discovery might just rewrite the rules of motion once again.